Welcome to our third lecture on partial differential equations. Previously, in the first lecture on partial differential equations, we had an encounter with the heat equation. In the second lecture, we recapitulated a few tools in the theory of Fourier series. And now we will apply the techniques in Fourier series to actually solve the heat equation over a finite interval. So let's recall the heat equation that we've seen previously. To model the heat evolution over a one-dimensional bar, let's say of length L. And in this setting, we will use homogeneous Dirichlet boundary conditions. And so the entire system that we consider looks as follows. We want to find the heat distribution uxt depending on position x and time t. And we have that the time derivative of u d over dt uxt minus kappa u prime prime xt, where u prime prime denotes the second derivative in space, equals f of x and t. And that is true for all x in between 0 and L, and for all positive times t. That is the partial differential equation we want to solve. Then also we have got initial conditions, which describes the initial heat distribution. When t equals 0, then we've got ux0 equal u0 x, where x is in between 0 and L again from the interval. And finally, we've got boundary conditions. And as already mentioned above, we use homogeneous Dirichlet boundary conditions. u0t equals 0 and ult equals 0 for all positive t. Now, the basic questions that we will answer in this lecture are whether the solution actually exists and whether the solution is unique. In fact, the second question, whether the solution is unique, is much easier to answer, and so that's what we're going to do first. So let's discuss the uniqueness of the solution of the heat equation. We use a standard technique to show the uniqueness of the solution. Namely, we assume that we've got two different solutions, u1 and u2, that satisfies the same heat equation with the same boundary values and the same initial data. And then we will show that u1 and u2 actually are the same. To do that, we take a look at their difference. Let's call this v equal u1 minus u2. All we need to do is showing that v equals 0 for all positions and all times. Now, since u1 and u2 satisfy the same heat equation with the same source term and the same initial data and same boundary values, we already know that v satisfies another differential equation, namely the first derivative in time of v, d over dt vxt minus kappa times v prime prime xt equals 0 for all x in the interval and for all positive times. So v solves a homogeneous heat equation, where the source term is 0. Second, since u1 and u2 are the same at the initial time t equals 0, we already know that v equals 0 at the beginning. So vx0 equals 0 for all x between 0 and L. And finally, of course, v again satisfies the Dirichlet boundary conditions. It's 0 at the endpoints at all times. Formally, that means for all positive t, we have got that v0t equals 0 and vlt equals 0. So we got the information that v satisfies this version of the heat equation, where all the data terms are 0. And what we will do is we take the first equation, the partial differential equation satisfied by v, multiply it by v itself, and then we integrate in space. So let's first multiply it by v. Then we have got d over dt vxt multiplied by vxt minus kappa v prime prime xt times vxt equals 0. Now we integrate in space. The integral from 0 to L of d over dt vxt times vxt dx minus kappa times the integral from 0 to L of v prime prime xt times vxt dx equals 0 again. That is true for all times t. And here we just integrate in space. Now the trick is that we can manipulate the last two integrals. Let's take a look at the first integral, where we integrate in space and we integrate the time derivative of v against v itself. Now a sharp look reveals the following. The integrand in the first integral actually is a derivative. Namely, if we take a sharp look, we see that the integral from 0 to L of the t derivative of v times v itself dx can be written as the integral from 0 to L of 1/2 d over dt of the square of vxt. That's what we do in the second line. And there we have that the integrand can be written as the derivative of a square of the function v. Now, the integral only takes place in space, and that is why we can pull out the time derivative from the integral. Of course, we can also pull out the factor 1/2. That is how we manipulate the first integral. Now let's take a look at the second integral. If we integrate in space from 0 to L v prime prime xt times vxt dx, we can use integration by parts in order to pull over one derivative of v onto the other factor. Formally, the integral from 0 to L of v prime prime xt times vxt dx equals v prime xt times vxt evaluated at x equal L and x equals 0 minus the integral from 0 to L of v prime xt times v prime xt again dx. Now, because of the boundary values, we readily observe that vxt equals 0 for x equals 0 and x equal L, no matter what time t. So, the boundary values just vanish, and so we can express the integral as an integral of v prime against itself. Let's summarize that. Plugging in those two manipulations, we get that 1/2 of the time derivative of the integral from 0 to L in x of vxt square plus kappa times the integral from 0 to L in x of v prime xt square dx equals 0. How does this help us? Well, let's first observe the following. The second integral is non-negative. The integral of the square of v prime is non-negative because we integrate a square. But then this formula means that the derivative of the first integral cannot be positive. It must be either 0 or negative. That leads to an important revelation, namely, the following integral is non-increasing in time. The integral from 0 to L of the square of vxt dx for any time t can be not increasing in time. At this point, you should consider that integral as a function in t. And what we know is that this function in t does not increase over time. It can only be 0 or negative. Well, that being said, this integral is not negative because it's the integral of a square after all. It can only stay constant or go down. So the lower limit of that integral is certainly 0, but at the same time, at the start time t equals 0, we already know that this integral is 0. That can be obtained from the initial conditions. For t equals 0, the integral from 0 to L of the square of vxt is just equal 0. And since this is non-increasing in time, but also non-negative, it must stay 0 for all times. We see that at all times t, the integral from 0 to L of vxt must be 0, but that can only be true if at all times the function v itself is 0 for all x between 0 and L and for all times t. So going back, since the function v is 0 at all positions and all times, that also means that the difference between u1 and u2 must be 0 at all positions and all times. That is, u1 and u2 are the same everywhere and always. And that has to be shown. So the solution obviously is unique. Okay, so far we've proven that the solution, if it exists, is actually unique. And the most important question is whether the solution actually exists at all. We will show the existence of a solution by actually constructing it explicitly from the data, from the initial values and the source term. The technique that we use for that purpose is the technique of Fourier series. So, since the solution comes from the data, let's first take a look at the data and assume that both the source term f and the initial values can be represented as a Fourier series. Now, the function f, of course, generally does not only depend on x, but also on space, but also on time. Which means if the function f can be represented by a Fourier series, actually the coefficients will also depend on time. So if we represent f as a Fourier series at all times, we have that f(xt) equals af0 of t, the constant term, which depends on time, plus an infinite sum, starting at n equal 1, going up to infinity, and involving the following summands. We have got afn of t times the cosine of 2 pi n x over L plus bfn of t times the sine of 2 pi n x over L. Here the coefficients afn and bfn again are dependent on time. Similarly, we've got a Fourier series, or we assume to have a Fourier series for the initial data. Well, since the initial data u0 do not depend on time, again we have got the more classical situation where the coefficients are also fixed and not time dependent. So we write the Fourier series of the initial data u0 as follows. u0 x equals a0 0 plus the sum starting at n equal 1 going up to infinity of a0 n times the cosine of 2 pi n x over L plus b0 n times the sine of 2 pi n x over L. In the latter case, and we emphasize again, we are dealing with constant coefficients. Now, since we already have expressed the data of the problem as a Fourier series, we will also try to do the same thing for the solution u itself. uxt will be written as follows. uxt equals a0 of t plus the infinite sum starting at n equal 1 up to infinity of an of t times cosine 2 pi n x over L plus bn of t times sine 2 pi n x over L. And here again, the coefficients in that Fourier series actually depend on time, since the function u itself is also time dependent. Now, with all that said and done, there's one big reveal, namely the Fourier series that we will use for the source term f, the initial data, and also the solution itself will not be a generic Fourier series, but more specifically, we will use a Fourier sine series. The explanation for that will follow shortly. So specifically, we will henceforth assume that the coefficients a all vanish. Formally, for all n starting at 0, we have got an equal a0 n equal afn all equal 0. So the only terms that remain will actually be the sine terms in those Fourier series. Why is that a good idea? Why is that a natural idea?
So why would we use a Fourier sine series? Why couldn't we just use a Fourier sine and cosine series? Well, to appreciate that choice, let's go a few steps back and recapitulate that the Fourier series is used to approximate periodic functions. Right up to now, we've been working only over an interval from 0 to L. So in order to use Fourier series, at least formally, we need to cross over into this domain of periodic functions. So what we can do, of course, is we can use some fairly arbitrary periodic extension of the original functions. Let's suppose we've got some solution of the heat equation, depicted here in this graph. First, it's only defined over the interval from 0 to L, and it satisfies the Dirichlet boundary values. So let's suppose I take an odd extension of this function, also depicted here already. If the original function has got two derivatives within the interval, then also the function that we obtain by periodic extension, this periodic function depicted here, will have two derivatives within each of those intervals. What we see here is an odd extension, and let's take a look in particular at the interval endpoints, which now repeat over and over again. If you look closely, you realize that the function has got a derivative there. It's differentiable there. That is because we've chosen an odd extension. If we take derivatives over the entire real line, then we get a continuous function. Again, it's because we've chosen an odd extension, so that at the interval endpoints, this periodic function is always differentiable. Okay, we get a continuous function, and now if we take one more derivative, we get a piecewise continuous function. In particular, if the proposed solution to the heat equation at any point in time can be represented by a Fourier series, so can its first derivative at x and its second derivative at x. After all, we know that with Fourier series we can represent periodic piecewise constant functions. Okay, that seems a natural choice. What happens if we had chosen an even extension instead? The problem with choosing an even extension becomes apparent immediately. If we extend the function periodically via an even extension, then its first derivatives again will be periodic, but this time with jumps. And so we cannot take the second derivatives. Similar arguments also apply to any other choice of periodic extension. Unless we choose an odd extension, we always run into the same type of trouble. And for that reason, it seems most natural to use a Fourier sine series.
After this interlude, let's get back to our partial differential equation. Since we represent the solution u by a Fourier series, it would also be helpful if we can represent the derivatives of u as a Fourier series. And that is done on this slide. We do some simple calculations, and for example, the first time derivative of u, d over dt, u xt, can be represented by a Fourier series, and that's very simple actually. It's the infinite sum starting at n equal 1 up to infinity of b prime n of t times the sine of 2 pi n x over L. How did we get there? Well, since we take the derivative of u in time, we just distribute the derivative over all the summands in the Fourier series. And then we notice, okay, the Fourier modes, the sine terms, actually do not depend on t, they only depend on x. So nothing happens there, but the coefficients depend on time, and then we take, of course, the time derivative of the coefficients. That's what we have done here. So if we want to take the time derivatives of the Fourier series, we just take the time derivatives of the coefficients. Next, we take a look at the derivatives in x of first and second order of u. In the second equation, if we take the derivative of u in x, we get the infinite sum starting at n equal 1 up to infinity of bn of t times 2 pi n over L times the cosine of 2 pi n x over L. In that case, okay, again we distribute the x derivative over all the summands in the Fourier series, and we notice on the one hand the coefficients do not depend on x. Nothing happens there, but the sine modes of course depend on x, and so we just compute their derivatives in x. And we repeat this for the last line, we take the second derivative of u and x, and simple calculations now lead to the following. That equals the infinite sum, starting at n equal 1 up to infinity, of bnt times negative 4 pi square n square divided by L square times the sine of 2 pi nx over L. Now let me remark that with these calculations, what we actually do is we express the derivatives of u in terms of Fourier series. We can just easily read off the coefficients now. For example, the first time derivative can be represented by a Fourier sine series, and the coefficients are b prime n of t. And similarly, we will use the second derivative of u and x, and that again can be used as a Fourier sine series, where the coefficients are b and t multiplied by negative 4 pi square n square over L square. Having gathered this information about u and its derivatives, how we can express them in terms of Fourier series, let's see how we can apply this to the partial differential equation and the initial data. We know the Fourier coefficients of the initial data and the source term. We have got formulas for the coefficients of the solution. And now we want to relate all these coefficients using the partial differential equation. Let's see how we can do this. We recall that for any function, we can actually extract the Fourier coefficient. We just need to multiply it with the corresponding Fourier mode and then integrate. That's what we do with both sides of the partial differential equation, of the heat equation. So let's suppose we take the nth Fourier sine mode, multiply it with both sides of the heat equation, and integrate this. We have the integral from 0 to L of the first time derivative of u in xt times sine of 2 pi nx over L dx minus kappa times the integral from 0 to L of the second x derivative of u xt times sine 2 pi nx over L dx, and that equals the integral from 0 to L fxt times sine 2 pi nx over L dx. That is true for all times t. And remember that multiplying against the Fourier sine modes and then integrating produces the coefficients. Each multiplied then with 2 over L, but this doesn't matter here. So up to the factor 2 over L, the first integral produces b prime n of t, because that, after all, is the nth Fourier coefficient of the first time derivative of u. Similarly, the second integral produces bn of t times negative 4 pi square n square over L square, which is the nth Fourier coefficient of the second derivative in x of u. And of course, on the right-hand side, we just get the nth Fourier coefficient of the source term f, bfn of t. Substituting that, we extract the following differential equation. b prime n of t minus kappa bn of t times negative 4 pi square n square over L square equals bfn of t. So we obtain a first-order differential equation that is satisfied by the nth Fourier coefficient of the solution. On the right-hand side, bfn of t is just part of the data, and on the left-hand side, well, we have got the unknown coefficient bn and its derivative. So it is an ordinary differential equation. Similarly, we can proceed with the initial data. So we would like to obtain initial data for the nth Fourier coefficient at time t equals 0. Well, we know that at time t equals 0, ux0 equals u0 of x. If you multiply that identity with the nth Fourier sine mode, integrate again, we get the following. The integral from 0 to L of ux0 times sine 2 pi nx over L dx equals the integral from 0 to L of u naught x times sine 2 pi n x over L dx. Again, both sides of this equation extract a Fourier coefficient each. On the left-hand side, we get bn0, and on the right-hand side, we get b naught n. And that produces the initial condition of the ordinary differential equation for the nth Fourier coefficient, bn, of the solution to the heat equation. So to summarize, the ordinary differential equation and its initial condition read b prime n of t plus kappa bn of t times 4 pi square n square over L square equals bfn of t with initial condition bn 0 equals b naught n. So we have got a first order ordinary differential equation that we want to solve, and we have got the necessary initial data. To solve this ordinary differential equation, to solve this ODE, we can just use anything in our toolbox to solve ordinary differential equation. For example, we can use the Laplace transform, or we can look up the solution formula. In either case, the solution looks as follows. We have got bn of t, the nth Fourier coefficient at time t, equals b naught n times the exponential of negative 4 kappa pi square n square over L square times t plus the integral from 0 to t bnf of s times the exponential of negative 4 kappa pi square n square over L square times t minus s ds. The solution formula neatly separates the influences of, on the one hand, the initial data, and, on the other hand, the source term.
Let's see how this works out in action. Suppose my initial heat distribution is again a piecewise constant function that switches between the values 0 and 1. I start the heat evolution, and what we see here is the development of the heat evolution over time, where the solution is approximated by a partial Fourier sum. In this case, it's up to 200 terms, and this is already enough to produce a convincing picture. As expected, we see that the heat smoothed out over time. And as the second derivatives of the graph of the heat equation get smaller and smaller, also the speed of the heat evolution gets slower and slower. After some time, we can barely distinguish anymore whether the graph is moving or not.
So let us summarize the procedure. First, we compute the coefficients in the Fourier sine series of the initial data and the source term. So we got some representation. U naught of x equals the infinite sum from n equal 1 up to infinity of bn naught times sine 2 pi n x over L, and fxt equals the infinite sum from n equal 1 up to infinity of bnf of t times sine 2 pi n x over L. Now, having obtained the Fourier series of the data, we get the Fourier coefficients of the solution u. For each frequency n, we solve the corresponding ordinary differential equation and thus obtain the coefficient bn of t. Having obtained those coefficients then, at the very end, we can easily assemble the Fourier sine series of the solution. uxt equals the infinite sum of bn of t times sine 2 pi n x over L. At this point, some very general remarks. Throughout those calculations, we have always used the full Fourier series, but instead, of course, we could also just have considered the partial Fourier sums up to some index n. And then we just solve for the coefficients b0, b1 up to bn. That would then provide an approximate solution. In fact, it's very much within the line of thinking how to solve partial differential equations numerically on a computer. And, well, since we have considered the full Fourier series, which are infinite sums, technically we also would have to consider the convergence of those sums. But as mentioned earlier, this is not within the scope of this lecture. Let me just remark that when the coefficients of f grow very widely over time, then it might happen that the Fourier series of u does not converge. And towards the end of this video, we'll finish off with the following remark, which is also an example. Namely, what happens if you've got a constant source term? We have mentioned earlier that in the case of constant data, the solution of the heat equation converges to a steady state solution. Now that we've got a solution formula, we can make this actually explicit. Recall that Bn of t equals Bn0 times the exponential of negative kappa pi square n square over L square times t plus Bfn times the integral from 0 to t of exponential negative 4 kappa pi square n square over L square times t minus s ds. Let's do a minor change to the last integral. The integral from 0 to t of exponential negative 4 kappa pi square n square over L square times t minus s ds can be rewritten with a change of variables. Then we get the integral from 0 to t of the exponential of negative kappa pi square n square over L square times s ds. It's now a fairly easy exercise to compute that integral explicitly. It equals L square over 4 kappa pi square n square times 1 minus the exponential of negative 4 kappa pi square n square over L square times t. And so, in the case of constant data, the coefficients of the solution Bn of t takes the following form. Bn of t equals b naught n times the exponential of negative kappa pi square n square over L square times t plus the constant coefficient of the source term Bfn times L square over 4 kappa pi square n square times 1 minus the exponential of negative 4 kappa pi square n square over L square times t. And now that solution formula, again, which is valid for the case of constant data, reveals that the solution converges to a steady state as t goes to infinity. That is easily verified. Take a look what happens as t goes to infinity in the last equation. The first term in the last equation corresponding to the initial data converges to 0. Because, okay, exponential of negative times a constant times t goes to 0 as t goes to infinity. In the second term, however, the term in the brackets goes to 1 as t goes to infinity. So the limit of Bn of t as t goes to infinity is Bfn times L square times 4 kappa pi square n square. That finishes our discussion of how to solve the heat equation with Fourier series. As a coda to this video, let's take a look how, in the long run, an initial heat distribution converges to a steady state. Again, we take a look at a heat distribution that is initially 0, but then gets charged up, so to speak, by a constant source term, which is piecewise constant it is 0 in the proximity of the endpoints of the interval, but constant equal 1 within a centered slice of the interval. And as we let the heat evolution run over time, we see that eventually it converges to a steady state. That steady state solution actually is the solution of another partial differential equation, which is known as the Poisson problem, and which is going to be the subject of the next lecture.